Hi everyone, my name is Shashank Goda and I'm here representing the team iHoop Insights. We are going to talk about injury prediction today. So the agenda for today's presentation is we are going to first talk about the introduction, then we are going to go over the data, then we will see the initial data analysis which we did, then we talk about the statistical significance, then we talk about the model which we created to predict whether a player is will be injured or not, and finally the key takeaways and recommendations which we can give to ensure that player can be player's injury can be rectified easily or take measures for the same. Coming to the introduction, our main objective for this project was to analyze injury risk in basketball players based on key performance metrics, identify and assess risk factors contributing to injuries, muscle imbalance, example muscle imbalances, performance metrics, and provide actionable insights for injury prevention strategies. Let's talk about the data. We have three data sets. In each of the data sets, we have session, muscles, and injury. So my main aim was to combine these three data sets. So we have created a key, which we are going to talk more in the further slides. But based on this key, we were able to merge all the three data sets. After merging all the three data sets, we have around 2,604 records, and for 14 unique players. The date range is from January 1st, 2023 to December 30th, 2023. These are some key columns or features which we can see in performance metrics. We have distance, speed, jump load, heart rate. In muscle imbalances, we have hamstring to quad ratio, cough imbalance, etc. In injury information, we have injury type, body part, and recovery time. Before we move on to exploratory data analysis, I want to see how we created a key. So we have a date column in all the three data sets. So we thought date would be the perfect thing to join with. Not exactly date, we extracted month and year. So again, we converted session date and date recorded columns in both sessions data set as well as muscle data set. We created a join key by combining player ID, month, and year of their respective date columns. And this key is to merge both data frames on the join key. We use a left join. And finally, we were able to combine both sessions and muscles dataset. Similarly, we had injury date. We extracted month and year from injury date, and we do have a player ID from in injury dataset too. So we created the similar key in injury dataset, and now we were able to merge all the three datasets based on this key. So that's how we joined the three datasets. Now moving on to our exploratory data analysis. We have the injury rate here, around 226 injuries, which is around 8.68% injury rate. Hamstring to quad ratio and muscle imbalances are the significant predictors of injuries. Position analysis, guards appear to have higher injury risk based on risk scores, and injury type, muscle strains, and tendonitis are most common injuries. So let's quickly go to our first chart here, where we are going to see the injury distribution based on position. You can see from the chart, the bar chart shows the distribution of injuries across different player positions, guard, center, and forward. And apparently, guard positions have the highest number of injuries, followed by center and forward with the least. Just to just a quick refresher on the positions. The ones which are marked in red are guard. Those are marked in red based on our initial data analysis. Apparently, most of the injuries happen for the guard position. The yellow are the ones are in medium risk, and these positions are known as center. And the ones which are in the green are forward, and these appears to be the lower risk areas based on our initial data analysis. Coming to our top 10 most common injury types, the bar chart shows the top 10 most common injury types. The most common injuries are tendonitis and strain, followed by concussion and sprain. This visualization actually helps us to identify most frequent injury types, providing insights for injury prevention and focused player care strategies. So, moving on to some key metrics distributed for injured versus non-injured players. Here we are analyzing the distribution of key performance metrics for injured versus non-injured players. Uh, for each of these metrics, we have a violent plot that compares the distribution between players who have an injury and who doesn't have any injury, and each plot is compared with each other. Let's talk about few of the insights. First, we are going to talk about the first three charts, distance in miles. The distribution of distance covered by injured and non-injured players appears to have some overlap, whereas for speed max, there is a clear separation between injured and non-injured players, with non-injured players generally achieving higher speeds. When we talk about heart rate max beats per minute, the distribution of maximum heart rate shows a broader range for non-injured players, whereas injured players seems to have more concentrated range. Moving on to the next three charts, the TRIMP, also known as training impulse. Non-injured players show a higher variance in TRIMP values compared to injured players, indicating a higher intensity or variation in their training sessions. Accumulated acceleration load. Injured players tend to have a higher accumulated acceleration load, which could be related to physical strain they experience during play. Coming to the jump load. Injured players have more concentrated distribution of jump load, possibly suggesting that they are more prone to injury due to the higher exertion in jumps. Let's talk about the last chart, which is hamstring to quad ratio. The distribution shows that the hamstring to quad ratio is generally higher for non-injured players, which could suggest a more balanced muscle strength ratio that may protect them from injury. Again, these insights can be used to understand the relationship between performance metrics and the likelihood of injury, which aids us in injury prevention and performance optimization strategies. Let's move on to the next slide. Here we are going to talk about injuries over time. So this line chart shows the trend of injuries over time, which with fluctuations observed throughout the year. The number of injuries seems to peak during mid-year with sharp drops in between, particularly in the months of January and December. Again, there isn't any pattern here. This irregular distribution of injuries can reflect multiple factors such as seasonal factors, training cycles, maybe some few of the players have player fatigue and the game schedules. There are so many factors which can be inferred from this uh, chart. But again, this is just a quick line chart to understand which peak months do we have most injuries with. Let's move on to correlation analysis. Here you can see in the right hand side is the correlation matrix of key metrics. We have all the key columns here and the correlation analysis for each of these key values. So few insights here. We do have some strong positive correlation. The muscle imbalance percentages such as quad imbalance percent, hamstring imbalance percent, calf imbalance percent, groin imbalance percent are highly positively correlated with each other. This suggests that the players with higher imbalances in one muscle group tend to have higher imbalances in others too. With some injury related insight, we have had injury, which shows a moderate negative correlation with performance metrics such as speed max and heart rate max BPM, suggesting that the injured players may exhibit lower performance in these areas. There is a weak correlation between head injury and other performance related metrics such as distance in miles, trim, and jump load, suggesting that these metrics do not strongly predict injury status. And finally, a few imbalance performance relationships. The imbalance metrics such as quad imbalance percent, hamstring imbalance percent show moderate correlations with performance metrics such as distance in miles, speed max, which could indicate that the muscle imbalance may affect overall performance. Again, this correlation matrix helps identify the interdependencies between different performance and injury related metrics, which assist us to understand the factors which might influence player injuries. Going on to the next slide, we did statistical significance testing using t-test to compare key metrics between injured and non-injured players. Again, we took few of the columns, few of the features, and we split the data into two groups, one for players with injuries and another for players without injuries. The t-test is applied to both of these groups and the p-value is calculated for each metric. So we wanted to see whether there was any statistically significant difference between injured and non-injured players. Based on our statistics, there isn't any significant difference between both of the players in for this matrix. So let's move on to the next slide. And this is the slide where we created our model. We created a random forest classifier to predict injury risks. Based on our initial data analysis, we saw that some few features were highly correlated, such as muscle imbalance percentages. So we should just keep one from each group to avoid redundancy. Also, hamstring to quad ratio was identified as significant, so we retain it. And obviously, here our main target is head injury column. It's 1 or 0. It's a classifier model. And in the back end, we applied SMOTE for class balancing, which is appropriate. And we do have few moral parameters. Max depth, we kept it as 5. And for evaluation metric, we are going to uh, use ROC AUC and classification report for performance evaluation. We created two models. So I'm going to talk more about model 2 because model 1 was just a initial model for testing. When we go to the model 2, you can see it's an improved model, and you can see in the next slide where we are okay, for this slide these are the key features. We can see that the quad imbalance percent, calf imbalance percent, and hamstring to quad ratio are the key factors which are these features are very important to predict whether a person has, whether an athlete has uh, injury or is more prone to injury. Okay, let's quickly talk about the insights. This classification report, we can see here, shows a higher recall. It is a higher recall. Shows higher recall of 0.84 for identifying injuries, indicating that the model is good at identifying true injuries. Coming to the ROC AUC score, we have it around 0.90, which indicates that the model is good at distinguishing between injured and non-injured players. We do have cross-validation ROC AUC scores too, which are consistently high with a mean score of 0.94, suggesting that our model is performing stable across different data splits. Coming to the threshold adjustment, we kept the threshold as 0.3. So after adjusting the threshold to 0.3, the precision improves significantly for injured players, and the precision for injured players drops to 0.13, while recall becomes 1, meaning that the model is now able to correctly identify all injured players with less false positives. And coming to the adjusted ROC AUC score, which is slightly low at 0.89, but again, uh, it is a good score as we are able to still distinguish injured players and non-injured players. Coming to next slide, this is we are going to talk about the risk assessment for the players. We calculated a risk score for each player and assigned it to each player to understand, to categorize the players into 3 or 4 domains. In the next slide, we can see what are these domains. Yeah, we have risk levels as very low, low, moderate, and high. So this I have a quick example of high risk players here. Malik Robinson, guard, who has a risk score of 0.76. Brandon Mitchell, who's also a guard, has a risk score of 0.75. Anthony Lopez, who is a center, has a risk score of 0.72. We do have a risk level distribution by position. Guards are the distribution of guard is from 0.2 to 0.7. However, the higher score is higher average score is for forward, which sort of conflicts with our information about in our initial data analysis that the forward are safe, but as per our model, and the risk score which we gave the forward is also prone to injuries. And our code actually outputs a CSV file. This is the output of the CSV file which we have after running our model prediction. So each these are the top 10 most risk players who are prone to injury. We have a risk score assigned to each of the player. So this has player ID, name, position, risk score, and their hamstring to quad ratio, quad imbalance, and calf imbalance. We are going to submit this file along with the submission. So few key takeaways. We know that the muscle imbalances, especially quad and calf, are the most significant contributors to injury risk. Guards are at a higher risk compared to forwards and centers, and which is again, forwards are also more prone to injuries, as we just saw from our model. Injury prevention strategies should focus on improving muscle imbalance, particularly in the hamstring to quad ratio. And our injury risk model is effective for identifying high risk players, but again, we can optimize the model to change our parameters. And coming to our final insights, based on the results from both initial data analysis as well as our model predictions, we were able to conclude the following. We do have high risk players. Players in guard and forward position tend to have the highest risk scores. Again, this indicates that the guards might be at a higher risk for injuries in this set, particularly given their high hamstring to quad ratio, quad imbalance, and calf imbalance. There are few risk factors. The hamstring to quad ratio, quad imbalance, and calf imbalance are the key contributors to a player's risk score. High risk players with a risk score of 0.7 or above typically have significant higher values in these metrics. And the overall distribution, the distribution of risk levels is relatively skewed towards high and moderate categories, with only two classified as very low risk. Maybe having old data such as 2022, 2021 will be able to define or have a more proper distribution of the risk levels. And few recommendations which we are going to give to the committee. So focus on muscle imbalance rehabilitation, targeted exercise to address quad and calf imbalances. So position specific training. We do know that the guard and forward are more prone to injuries, so maybe customize injury prevention strategies for guard and forwards who are at a higher risk. And as usual, we need to have a proper monitoring system, so which again, regular assessment to track players injury risk levels and adjust training plans accordingly. These are our recommendations to the committee. And finally, thank you for your time and listening patiently to this presentation. There is a detailed analysis present in the Jupyter notebook file, which we are going to submit along with this presentation. So we're going to submit this deck along with a Jupyter notebook file and a CSV file of high risk players and a normal risk assessment score for all the players. That's all from our side. Thank you.